As we saw in class this week, Chapter 7 is about bonding theories. And we started with valence bond theory, and in particular looking at how valence bond theory describes how a central atom forms hybrid orbitals in order to accommodate the bonding that it wants to be able to do, as well as to be able to accommodate lone pairs. Let's look at a few of the application questions from Activity 7A. I have here carbon tetrachloride. Notice that the carbon has 4 electron domains around it, 4 regions of electron density. That's going to make the carbon tetrahedral. So I'm going to draw the molecular shape. So that's the basic molecular shape around the carbon. If the carbon has a tetrahedral electron geometry, then its hybridization will be sp3. And so if I want to draw the hybrid orbitals around on the carbon, I'm going to draw one pointing along that direction of the tetrahedron, one here, one going back, and one in the front. Are there any remaining p orbitals? The answer is no. Because we have used sp3 hybrid orbitals, we've used up all of the p's, so there are no p orbitals. Now, what does this tell us about the carbon? This tells us that this carbon is ready, at least it has 4 hybrid orbitals, and those hybrid orbitals can either form bonds or they can contain lone pairs. And in this particular case, we can see that they are going to form 4 bonds, with one with each chlorine. And we can recognize that the 4 valence electrons of carbon, we will put one electron in each hybrid orbital. If we look now at water, we can look at the central atom of water, which is oxygen. We see that it has 4 regions of electron density around it, 2 bonds and 2 lone pairs. So if we sketch its geometry, we can say there's going to be a lone pair and 2 bonds to the hydrogens, right? So that's a sketch of its geometry. If there are 4 regions of electron density around the oxygen, that means it's going to have a tetrahedral electron geometry, and that again means that the oxygen will be sp3 hybridized, and while we're at it, we'll just say there are no p orbitals. If we were to draw those hybrid orbitals, we need to draw them in a tetrahedral shape. One is going to be coming out in the front, one will be behind, one will be here, and we'll end up putting our lone pair in it, and the other one will be there. How many valence electrons are there in oxygen? Well, oxygen has 6 valence electrons. Let's see where they end up. One is here, one is here, one is here, one is there. So there are 2 lone pairs, that accounts for 4 of them. One is here, and one is there. So let's be clear, all we've drawn so far is the oxygen's orbitals and the oxygen's atoms. And what we can see is this hybrid orbital, which is an sp3, and this hybrid orbital, which is an sp3, are prepared to form a bond because each one is half filled. We have not drawn the bonds yet, but right now we're just drawing the hybrid orbitals on oxygen. I'm going to skip this example because we did it in class, but the key is posted if you want to look at it. Let's look at the nitrogen in this compound. We can see that it has 3 regions of electron density, a double bond, a lone pair, and a single bond. So if we were to sketch the geometry, we will draw the nitrogen. There's 3 regions, so it's going to be a trigonal planar arrangement, and I'm going to draw it so that I've got one component of the trigonal planar in the plane of the paper, one going back, and one coming forward. And I'm going to put the lone pair out there behind, I'm going to put the carbon out in front and the hydrogen over here. So that's what we know about the nitrogen's geometry. If the nitrogen is trigonal planar like this, then we can also say that it uses sp2 hybridized orbitals, and there is one p orbital that's left. Let's draw the sp2s. The sp2s are going to be collinear with the bonds, or in this case with the lone pairs. So all three of those are sp2 hybrid orbitals. There's a leftover p. The leftover p is going to be perpendicular to the plane of the trigonal planar sp2 hybrid orbitals. Nitrogen has 5 valence electrons. We've already drawn 2 of them. 2 of them are in this lone pair here. I'm going to put 1 in the p orbital, 1 in that sp2, and 1 in that sp2, for a total of 5 valence orbitals. Sorry, 5 valence electrons. Notice which orbitals are ready to bond. The p orbital is half filled, it's ready to bond. This hybrid orbital is half filled, it's ready to bond. This hybrid orbital is half filled, it's ready to bond. This one is full, so it can't bond. But nitrogen, notice, needs to form 3 bonds over here. And we've got 1, 2, 3 orbitals that are ready, so that looks good. If we move down and look at the carbon in that same molecule, we can do the same analysis with carbon. Carbon has 3 regions of electron density around it, which means the carbon is going to be trigonal planar. So let's draw that geometry. So here's the trigonal planar arrangement around carbon. If it's trigonal planar around the carbon, then we also know that it is sp2 hybridized and that there's 1 p orbital left. Let's draw the hybrid orbitals. There's going to be 1 pointing in this direction, 1 pointing in this direction, and 1 pointing in that direction. Let's actually finish to figure out what this is. Let's say the nitrogen is back here, and then this is a hydrogen, and this is a hydrogen. There's a p orbital that we need to draw. The p orbital is perpendicular to the sp2 hybridized orbital plane. So it's perpendicular to the trigonal planar arrangement of the hybrid orbitals. And let's ask where the electrons are. There's going to be 1 electron of the carbon here, 1 here, 1 here, and then there will be 1 in the p orbital. Notice that that's 4 valence electrons for carbon. That means carbon right now has 4 orbitals that are poised for bonding. Recognize that this p orbital, which is now, if you think about combining these two, this p orbital and this p orbital are parallel to one another, which is going to allow them later to form a bond. This sp2 orbital is pointing right at this sp orbital, and that's going to allow them later to form a bond. One of the things to recognize is that even though when you look at it you think, oh, this nitrogen is going to look totally different than this carbon, they're different atoms, etc., is that notice both of these are sp2, both of them have a p orbital left, and so the picture of the hybrid orbitals looks pretty similar. What's different is whether there are electrons, is how many electrons are in there. Let's do one more. If we take the carbon in HCN, we recognize that carbon has 2 regions of electron density. One is a triple bond, one is a single bond. That's going to mean that the carbon is linear. I'm just going to redraw it so that we have a little more space. So that's what the carbon is going to look like. If it's linear, that means it's going to have hybrid orbitals that are sp, and that means there's 2 of them, and then there are 2 p orbitals remaining. If you're not feeling confident about how to predict this, go back to the table on the first page of the activity 7A. Now, if we want to draw the sp orbitals, with sps, they come in a set of two. One will be pointing in this direction, the other will be pointing in that direction, so each of those is an sp. There are two p orbitals remaining. One is going to be perpendicular to the hybrid orbitals, but in the plane of the paper. And then one has a lobe coming out and then another lobe behind. So this is the one that would be kind of coming out of the plane of the paper at us. Carbon has 4 electrons. Where are they? Well, there's one in that sp. There's one over here in this sp. There's one in this p orbital and one in that p orbital. So notice that in this structure, carbon needs to form 4 bonds, which means it needs 4 hybrid orbitals, sorry, not 4 hybrid orbitals, 4 orbitals that are half filled with electrons. Here's one, here's a third one, and a fourth one. It's taken its 4 valence electrons and it's essentially remodeled its atomic orbitals into these new structures so that they're ready to form overlapping bonds with another atom. Let's get this one set up by looking at what the nitrogen would look like. The nitrogen also has 2 regions of electron density around it. So if we draw this bigger, the nitrogen has 2 regions, so it's going to use sp, and it's going to have 2 p orbitals left. And they're going to look just the same as the ones on the carbon, but the electrons will be different. So the orbitals will look the same, but the electrons will be different. So nitrogen will have 1 sp orbital going that direction, 1 sp orbital going that direction, a p orbital that is perpendicular but in the plane of the paper, and then another p orbital that is coming out at us. Nitrogen has 5 valence electrons. 2 of them are going to be in that sp hybrid orbital. That's going to be our lone pair. There's going to be 1 in this hybrid orbital. There will be 1 in this p and 1 in that p. So notice that in the structure, nitrogen needs to form 3 bonds. So it's got an orbital here ready to go, because it's half filled, an orbital here ready to go that's half filled, and an orbital here that's ready to go that's half filled. So 3 orbitals half filled, ready for bonding. And they, of course, are going to line up with the carbon orbitals and to overlap to form new bonds.